Hello, and thanks for listening in today. I want to acknowledge my co-authors, Rich Van Dock, Jeff Omvik, and Mark Sterling, all from Sterling Seismic, and Tom Bratton from Tom Bratton, LLC. So the talk outline looks like this. DAS reflection survey geometry. I'll just do a quick overview of the components of a DAS survey. Have a brief DAS VSP imaging discussion. And then we'll look at the meat of the talk, which is time-lapse reflection imaging with horizontal DAS fiber. And I also want to introduce a new fracture imaging potential technique with some showing some real data. And we'll briefly discuss a couple of engineering applications of this DAS reflection results, the type that we're seeing here. That's a hypothetical engineering application. And then we'll finish off with some conclusions and a review of the main points. So here's the components of a DAS survey. Here we have a surface seismic source, in this case Vibrosize, which would be the most common. We have a well bore with this DAS fiber going down and then turning horizontal and going out some distance on a horizontal. And then here at the surface we have what's called an interrogator laser system, which is basically the recording system. I'd like to just quickly talk about VSP. The meat of the talk here is mostly of looking at the data that we record down here on a horizontal well, but there's also all this fiber here in the vertical part of the well, which is where we normally have a VSP. And I just want to show what some results are from recording data and using data that's recorded in that vertical section. So we have a surface seismic source, wave field going down, being reflected off of interfaces here and being recorded on that vertical part of the cable. And generally, we get some really excellent results. We see zero offset VSPs, walkaways, and 3D VSPs recorded on DAS fiber, and it's really quite good. I'll just quickly show an example here of a 2D walkaway VSP that was processed by my co-author, Rich Van Dock. So this is about 2 kilometers horizontally here. This is a final 2D reflection image, pre-stack time migration. This is this vertical axis here is a time axis, two-way time, and so this axis here is, or this is roughly the target zone, as I understand it. So we're out, a kilometer and a third away from the wellbore here, and this is really very good VSP reflections. They're nice, crisp, high frequencies. And are about as good as we see in really the best 3-component surveys, 3-component geophone surveys. So we're really seeing some very good results. We and other companies are seeing some very good results out of DAS data. And so there's a really definitely a future in DAS recording for VSP. Now, for the most part, we're going to talk about in this geometry here, where we have, again, the wellbore. We're going to look at the horizontal DAS fiber down here, a surface seismic source up here, and then we're going to see the wave field going down, reflecting off of interfaces below the DAS cable, and then be recorded on the DAS cable. So we're going to be imaging below the DAS cable. Now, the geometry of having the surface source and the receivers down at very different elevations is a little bit difficult to process. It forces us to take an approach that is more time-consuming and more error-prone, which is more pre-stack time, or actually pre-stack depth migration. So rather than having our sources at the surface and receivers way down here, we take the approach of downward continuing the seismic sources down to the level of the DAS cable, so that now our sources and our receivers are at the same elevation. And then we process the data using typical CDP processing, data processing flows. We're able to use normal move-out analysis, statics, all the things you can use in surface seismic processing we're able to apply here. It makes things a lot easier and a whole lot faster, and we get some very good results out of it. So we're really we encourage this downward continuation approach when we're talking about reflection imaging using the horizontal DAS cable. So the example that I'll show you here is one in which we have there's the ground surface up here. We have a surface seismic sources, in this case Vibrosize. We had 96 shots at a nominal 150-foot spacing along a 2D line. little bit of crooked line, but it's nominally a 2D line. We had a well bore that went down to about 9,000 feet depth and then turned horizontal with a slightly toe up geometry. But of course there was a DAS fiber all the way along. The image space that we'll show here is the area below the DAS cable and doesn't quite cover the entire horizontal length of the well. And by the way, this well bore was only about 4,500 feet long, a little bit short, but that's what this well bore was. So this is the reflection image from the baseline survey. I'll give you a quick orientation here. This axis is two-way time in milliseconds, 10, 20, 30, 50, 70 milliseconds. This red line here is the location of the well borehole, the horizontal borehole. You can see it moves around, it's a little bit toe up. The trace interval here is 6.6 feet, and that's because the receiver interval along the DAS cable is only 13.2 feet. So we actually get a very close station spacing or good horizontal resolution with the DAS cable. The image length is about 4,155 feet, which isn't quite the entire length of the horizontal part of the borehole. This is about 325 feet here. I'll mention here that the maximum sweep frequency on the Vibra-size truck was about 120 hertz. We were able to push the frequencies here in excess of 100, close to 110 hertz in this interval, and say in the upper 50 milliseconds. So we get pretty good vertical resolution as well as pretty excellent horizontal resolution. Now, before I show you the time lapse image, I want to just draw your attention to two places here. One is this reflector, where you're going to see a lot of changes going from as we jump from one survey to the next. In particular, you're going to see a lot of changes in amplitude. It just looks more chopped up. And then this reflector right here actually kind of becomes discontinuous, and we see the reflector crawling up here and up the section. You see a gap right here in the reflection amplitude. I draw these because it's I can't flip back and forth in PowerPoint in this record mode, so I'll just have to go draw your attention to these reflectors as we go along. So here's this reflector, and here's this one right down here, and so keep an eye on those locations. So here's the baseline survey, and then here's the first time lapse. And so far, it's the only time lapse from this area, for this well. So again, we saw changes in these reflections. This reflection right here, and in particular, a really large one right there. So let's quantify. That's a qualitative way to describe this. Let's quantify what some of these changes are and make use of some of those quantitative values. So I measured the time delay between the wellbore location and this first reflecting interface down here, or I guess actually kind of the second reflecting interface. I know those reflecting interfaces didn't go anywhere. They didn't move just because of fracking. And I know the wellbore didn't change because of fracking, but the two-way time did change between the two of them. And so I used that change in two-way time to compute a percent change in interval velocity as a result of fracking and flow back in production. And that's this red curve here. We can see goes between plus and minus 5% changes, right? Actually, not quite that much, probably 2.5 to 3% below, or I guess close to 5% down here, and as much as 5% here. So in some places the velocity increased, in other places it decreased. This black curve up here is a production curve, an oil production curve that was derived from passive listening of the DAS cable, and this was done by a company that does this type of measurement all the time. So this is their oil production curve that they got by the passive listening to the DAS. You can see this is actually really spiky here, and incidentally, these spikes in production match almost perfectly with where the plugs were in the plug and perf completion for this well, indicating maybe we want to add some more plugs when we're doing production so that we can initiate fractures a little better. In any case, so we have generally increasing production here, drops down, increasing production here. Simultaneously, we have, with increasing production, we have decreasing compressional wave velocity as we cross that point again and we restart the cycle, decreasing shear velocity, or decreasing compressional wave velocity with increasing oil production. Now, we also, I didn't mention this before, but we also have, we're able to do shear wave reflection imaging. Because there's a lot of shear waves in the data, and shear waves they weren't the primary source. This actually was a compressional wave source, but because we do this downward continuation approach, it actually allows us to do reflection imaging with the shear wave. The shear waves are not as good a quality as the P waves, but good enough for us to at least do some time-lapse reflection imaging and measurement in these upper 60 milliseconds or so, a couple hundred feet. So again, we have a change in shear wave velocity in the red. Again, that's that compression, or this is the change in oil production as a function of location. And here we have the changes in shear wave. Now remember, with the compressional wave, the shear wave or the compressional wave velocity actually decreased with increased production. Here we have, in general, increase in shear wave velocity with increasing production. What does all that mean? Now, rock mechanicists have told us for a long time that there's a relationship between stress and strain and compressional and shear wave velocity. So, for example, in a plot like this, where we've taken a rock, put it into a rock squeezing machine, and we make these stress-strain plots on this stress-strain on these axes, which is the black curve here. As we increase the stress, the strain increases until the rock failure at this point. But we could also plot what happens to, say, the VP and the VS as a function of stress and strain. It clearly demonstrates that the compressional wave velocity and shear wave velocity are affected by changes in stress and strain. And we see that in our velocity analysis that we just did. This slide is a compilation of the S wave velocity changes, P wave velocity changes in the oil production. And these panels are each different regimes, if you will, about that have similar properties of the P wave and S wave velocity. And so let's look at a qualitative interpretation of what some of these are. So in this panel, for example, right here, our shear wave velocity has increased from the baseline. Our P wave velocity has decreased from the baseline survey. And all this indicates that with the shear wave velocity going up indicates that the fractures are closing. Shear waves are quite sensitive to the fractures. At the same time, again, the compressional wave velocity is decreasing or has decreased from the baseline. And that probably indicates that the fluid pressure is now below the bubble point. So we have bubbles going into solution that increases the compressibility of the fluid within the rock, and that lowers the compressional wave velocity. And in fact, we do know that the bubble point or the bubbles started going into solution in this reservoir. We'll quickly have a look at this one here. In this, we see that there's not very much oil production. By the way, these numbers are barrels of oil per day from each of these locations. So we see there's not a whole lot of production in this particular location. We have not much change in the shear wave velocity, but we do see an increase in P wave velocity. So not much change in the shear wave, probably not very well fractured. We don't see much change in the shear wave velocity. But our pressure remains higher than the bubble point. And so we have, so there probably is some pressure drawdown, and we probably have some closing of the fluid pores, or the pores in the fluid, or fluid space, the pore space for the fluids, and that increases the compressional wave velocity. So these types of qualitative interpretive tools can tell us somewhat about what's going on in the reservoir, and if we have even more information, then we can start to make quantitative assessments of how much pressure was drawn down. So I'd like to talk quickly about a new fracture detection method that may provide us some time-lapse capability to see where the fluids or the fractures are closing throughout the lifetime of the field. And this fracture detection that we're seeing in some of the data may lead us to some fracture imaging, actually be able to see where the fractures are and see maybe even be able to measure something about their width and so forth. So the situation here is, imagine we have a fracture here at depth, and we have a surface seismic source. Experiments like these have been done already and well done in the oil and gas industry. And they're generally called interstage fracture analysis, where they're running vibroseismic sweeps in between stages while they're fracking the well. What we're doing here is actually looking at fractures that have in a field where the well was fracked several months before, and so we've had pressure drawdown, we've had closing of some fractures and not of others. So what I want to show you here is a seismic shot record in which the source was off end from the toe, and we'll see the first arrivals coming along here, and we'll see the response of what I think may be a response to the existence of fractures. So here's that shot record. We see the first arrivals coming along like this. Again, the source was hit off the toe down here someplace. We see the first arrivals coming along here, and you'll see, if you look here, you'll see some kind of streaks that come opposite direction of the compressional wave, and several different places, and I'll mark these for you here with these red lines. And these events are just about the right velocity, certainly well within the margin of error, what we expect to be either S wave reflections, so downgoing P, downgoing compressional wave being converted to downgoing further downgoing shear wave reflections, so P to S reflections, or they might be just P being converted to S wave diffractions off of the rugosity of the fracture. So, but in any case, we see these downgoing shear waves, and they evidence that they're shear waves if they have the right velocity for doing this, for being shear waves. So the idea would be then that if these are in fact fractures that are being measured months after the completion of the well bore and months after the well has gone on production, then we have apparently some open fractures here. They might be natural fractures, or they might have been caused as a result of fracking. And if we do a time-lapse analysis on this data set, which I do intend to do, we'll see which fractures were there prior to the frac job and which ones were there afterwards. So this type of analysis will give us an opportunity to see how the fractures are changing through time from one survey to the next, and as a function of time as we go through production. So here's some ways to use this. Then I have this little hypothetical oil field here, or gas field. This is a map view. Our DAS cable, horizontal DAS cable, is this red dashed line right here. And maybe after a couple of 3D DAS surveys, we were able to cover or be able to see where we have pressure drawdown. That would be these blue areas right here. So perhaps we've got pressure drawdown. And I do show these as part of a 3D survey. And in fact, we can do this DAS reflection imaging in 3D if we have a 2D array of sources at the surface, just like we would with 3D seismic. Sort of like just a narrow spread shooting that we sometimes do with surface seismic. Imagine that we have this known pressure drawdown zones, and this would be useful if we were going to refrac that well. We'd want to probably put most of our effort into refrac into zones where we know there's no pressure drawdown, and therefore there's not been a lot of production out of these zones. But probably more importantly is if we're going to drill a nearby well, a new well, we want to be sure that we take that in these pressure drawdown zones into account as we plan this fracture. As we've planned the completion procedure. We don't want to just go pumping a bunch of fluid in here because we're just inviting a frac hit on this well, because it's well known that fractures are drawn toward lower pressure or lower stress regimes. So, and we also don't expect to see very much, if we're pouring frac energy and dollars into this side toward the low pressure zone, we aren't going to get the penetration into this side of the reservoir that we want, as opposed to maybe a zone like this where we don't have pressure drawdown nearby, and we might get more of this bi-wing frac that we're really interested in. So in conclusions and review of the main points, the DAS data provides a viable approach to time-lapse reflection imaging along a horizontal well. Time-lapse dash reflection imaging directly measures production-induced VP and VS changes. I think both of these points can be shown from the data above. DAS data may provide time-lapse information on fractures as they close with time, say due to sand embedment and pressure drawdown. Rock mechanics analysis of VP and VS changes can be used to estimate changes in pore pressure and stress depending on the known relationships between velocity and stress. With the proviso that in this last point, some parts of DAS interpretation will be qualitative because we will rarely have laboratory rock mechanics results from which to draw conclusions about stress velocity relationships. Thank you very much for your time.